Cool. Thanks a lot, Stefan. So, hi everyone. I'm Edwin. Today I'll be talking about my work, which is applications of dynamic Bayesian networks to study regime shifts and changepoint processes. So, just a brief outline of what I'm going to be going through today. I'm going to start off with some context. So, I'll talk about the theory behind ecological resilience and regime shifts, and then we'll talk about the key questions that surround the study of this topic. And then I'll be talking about the modeling methods that I'll be using to study this topic, and that is non-homogenous dynamic Bayesian networks, and also the integrated resilience assessment package. And I'll be applying this modeling method to two case studies. The first one is a very simple rocky shore system. It's very small, very simple. Then we'll be applying that to a fisheries ecosystem, which is significantly larger than both a spatial and temporal scale. And then I'll end with some key takeaways. So, ecological resilience, what is it? And this is the example that I always give. I'm pretty sure I gave it in 2019, gave it again in 2022, and here we are again. So, the ball in the cup, that is, imagine the ball in the bottom of the valley. This ball represents an ecosystem instability, which confers a set of ecological relationships that exist in equilibrium. Now, if I were to physically move the ball away from the equilibrium point, that would require some force, right? I had to physically push it. So in this context, the force would be disturbances or any natural perturbations. So therefore, we can then define ecological resilience as the ability for the system to resist disturbance while returning to its original position. That is resilience. Naturally, with resilience, there's going to be a threshold. Now, if we continue applying some sort of disturbance into the system, it's eventually going to reach some sort of threshold where it's going to fall into a new valley, and this enters a new stable state, which confers a new set of ecological configurations that is different from the original state. Now, a very simple, intuitive example would be coral reef ecosystems. In one state, at this equilibrium, this is regulated by a healthy feedback loop between corals and the algae that live in the coral that provide food for the coral. Now, with the increasing water temperature, once it passes a certain threshold, the coral will expel the algae, and then there's a breakdown of that feedback loop. It's no longer providing it food. And once it expels the algae, it enters a new state where it's essentially coral bleaching. The coral dies. And in this state, it's significantly lower biodiversity compared to the original state. So when it comes to studying resilience and stability, how do we quantify stability and resilience? So we spoke in principle that state one is one set of ecological configurations, state two, another set of ecological configurations. But can we quantify these relationships? And are there models that will allow us to recover these sort of links from empirical data? And then naturally, the second question would be, are there changes in the underlying dynamics of a system across two stable states? And can we recover and work out, okay, what's changing as state one approaches the threshold, and what's different, or what's actually changing between state one and state two? So these are open-ended questions that need to be addressed when studying this. So to address this, the modeling methods that I'll be using will be first, a non-homogenous dynamic Bayesian network, so DBN, to approximate non-stationary ecological processes. So we're using a non-homogenous DBN as opposed to a traditional DBN, because the traditional DBN assumes that the time series remains stationary over time, in the sense that the temporal processes or the time series processes, they do not change between time point A and say the end time point. But that wouldn't really fit well in a context of ecology, because as you see here, over time, things do change, whether or not there's a threshold. Then the second part would be to use non-additive modeling to quantify the relationship between system state and stressor. So we'll talk about the non-homogeneous DBN first. The model we're using is the Dynamic Bayesian Gaussian Mixture Bayesian Network Model, or just BGMD. And this is essentially just a non-homogeneous dynamic Bayesian network. And what it's doing is that it's introducing a change point process to divide the time series into segments, which may be more than one segment. And this allows for approximation of non-stationary ecosystem dynamics over time, while keeping edges fixed across segments. So in this example, imagine we have 4 time points. What we're doing is that we're recovering a dynamic network structure, but then working out, okay, at what point do the relationships change? And in this case, the model will works out that, oh, okay, between T3, T minus 3, and T minus 2, you got one set of relationships, interaction strengths, I should say. And at t minus 1 and t, that's a different set of interaction strengths. The next model is the integrated resilience assessment model, package even, and that was proposed by Vasilikopoulos et al. In 2017. And essentially, it's a three-step process. The first step is to apply principal component analysis into the system under study. And you're doing that because you want to derive system indicators through PC1. So in this area here, you can see PC1, there's a transition along the x-axis where it starts off on the negative values and then eventually it transitions to positive PC1. Then the second step would be to use this PC1 as your system variable and apply non-additive modeling. So in this case, they're using threshold general additive models. Essentially, it's just representing an abrupt change between response and explanatory variables at a certain point in time. So at one point in time, you have this relationship between x and y, and at a certain point, there's an abrupt shift and it fits another relationship between x and y. So once you have that, you can then approximate resilience of the given system as a sum of the distance between each point from the fitted line and sum that with the distance between each point to the fitted tipping point. And then you can derive the relative resilience of the system by dividing each value by the maximum resilience value of the system. And then you can interpolate everything to see a resilience landscape. So in terms of the modeling process, we'll be using the BGMD. I am doing 100 searches with a maximum of 2 breakpoints allowed. And then I'm going to be performing model averaging for the top 100 networks across the iterations. Then for the IRA package, it's essentially the same as I just outlined. We conduct PCA to derive system indicators. Then we use non-additive modeling. Then we perform resilience assessment. And with this two-step modeling framework, we'll be applying this across two case studies, a rocky shore boulder system and Adriatic fisheries. So the rocky shore communities, why are we using this? It's very simple. It has relatively low dimensions, so very few variables, but the amount of they have a high level of biological interaction. Additionally, through prior research, it has known links. Therefore, it's going to be a good system to test the ecological validity of the links that are found by our Bayesian network. And lastly, they have an experimental evidence of alternative stable states. And you can induce this regime shift through experimental manipulation. So given these three points, it's a very good starting point to test our modeling framework. So what do? We have 15 boulders with 3 experimental conditions. For 5 of them, we don't do anything. We just let it sit. For the next 5, we're removing 20% of the green seaweed. At the next 5, we're adding 20 top shells. So we're significantly increasing the grazing pressure on these 5 boulders. And data is collected at 2-week intervals, 6 times in total, which gives us a sampling time of around 3 months. So with the PCA, so dimension 1 is essentially a proxy for green seaweed. And as you can notice, with our natural change and 20% green seaweed removed, there's no real change. They're all clustered around here. But when we add 20 top shells, it starts off up here, where there's still relatively high amounts of green seaweed with high levels of DIM1. But then there's a big transition along the x-axis here. And another way to visualize this is just a different representation of the principal component. Again, there's no real change in the natural change condition or the 20% green seaweed condition. But with the 20 top shells added, you can see a step-like transition in this condition. So then we apply Bayesian networks onto it. So a change point was identified between week 6 and week 8 in all conditions, where across all 100 searches, they converge to this singular change point, even if I were to specify, hey, I'm going to give you a maximum of 2 breakpoints that I want you to work out, but they're converging to just one singular change point, which implies there's a change in interaction strength across all 3 conditions between week 6 and week 8. And then another thing to note is that the network structure becomes increasingly complex across the conditions, where in the natural change, there's only 7 edges, 20% green seaweed, there's 10 edges, and 20 top shells added, 16 edges. And in terms of the distribution of change points, I'm just putting this here because, as I said earlier, they all converge to this singular change point across all the iterations. And this will be very interesting to compare with a more complex network later. But just for now, this is just to show you how simple it is and the fact that it was able to converge to a single change point across every single iteration. So in terms of the network structure, in the natural change, you can see that there's a positive feedback loop between top shells, which is our grazers, and the green seaweed, which is the main thing that's dominating the boulder. And it starts off as a positive relationship, and this, after a certain point, so between week 6 and week 8, this relationship flips negative. Similar pattern in 20% green seaweed removed, with the only exception being that there are more edges. It starts off positive, 0.33 between top shell and green seaweed. And after that change point, it flips negative. But once we add 20 top shells, it becomes the opposite. It starts off negative, and then afterwards it flips positive. And what's probably happening is that in this first, because we're significantly increasing the grazing pressure in the first segment, it's going to be a negative relationship because higher levels of top shell will lead to lower levels of green seaweed. But after a certain point, because there's such low levels of green seaweed, that means there's less food for the top shells, and hence they both become positively associated in the sense that they both start to decrease over time. So to visualize this sort of shift, that's where the resilience landscape or the IRA package comes in. We have 2 fitted attractors, and when we put our natural change, you can see that there's no real change. Most of them are stuck in this upper resilience zone. There's one replicate where grazing pressure increases and then it falls to the lower attractor. This is the same pattern that we see when we remove 20% green seaweed. Most of them, there's no real change. It's clustered around this upper resilient attractor. And eventually, well, not eventually, one of the replicates, increased grazing pressure, goes down to the lower attractor. And lastly, we had 20 top shells added. They all initially start around in the upper attractor. It overshoots and it falls back to the lower attractor, and they both start going downwards to the it makes its way down the lower attractor. So we put them together. On one hand, our BGMD model, it's able to identify links consistent with prior knowledge of competitive interactions. And the change point processes that were identified reflects the non-homogenous ecological processes. And these are quite intuitive, and they're quite consistent with ecological theory. And with non-additive modeling, we're able to elucidate resilience dynamics of rocky shore system that were previously unknown. So this is a pretty good starting point. But of course, this is such a simple system with very low levels of variables. How will this fit? How will this work once we apply it to a much more complicated system? So the second case study is with the Mediterranean Sea fisheries. So why are we using this? It's because it's a biodiversity hotspot, and there's long-term documentation of human exploitation through overfishing and with the concurrent effect of ocean warming. And with all these together, and with the presence of historical time series, this is another very good natural laboratory to test our model as well. So we're focusing on the Adriatic Sea from the Mediterranean Sea. So we're taking monthly catch data from the Adriatic Sea, ranging from 1985 to 2013. And we have 8 species with 29 time points. And then we also are able to derive historical sea surface temperature data at monthly intervals. So with the principal component analysis, you can see that most of them start off at high levels of blue whiting, bogue, and picaros. Starts off around in positive PC1 values. And then eventually it shifts to negative values, where it's lower levels of blue whiting, bogue, and picaros, and high levels of anchovies and pilchards. And this is just to visualize the system indicator over time. You can see, for the most part, it stays in the positive PC1 area, and at some point it shifts negative. And so we know that there's a transition here. So how does this fit in when we apply the Bayesian network onto it? So first of all, let's talk about the change points. multiple change points were identified across iterations. You can see a lot of them, you have some at what 1990, some in 1992, some in 2000, and this is when I allow for 2 breakpoints to be identified. So here, what I did here was that I simply just took the highest proportion as our 2 breakpoints, and in this case, that is 1992 and 2000. So how does this look on the from the network perspective? So this is the original network between 1985 to 1992. So I'm not going to go through each individual link because that would probably take a while. So what I will focus on is what is changing between segments. So this is segment 1 between 1985 and 1992, 1993 to 2000. And I've added a plus and minus to show what's increasing, what's decreased. And you can see things are already changing. You have some links that are just increasing in interaction strength and some decreasing. And then from this segment to the next segment, you got even more changes. Now a lot of them have been either weakening or just there's just not much of a relationship anymore. And there's just an overall breakdown between the relationship, or I shouldn't say breakdown, there's a significant weakening of interaction strengths between variables that were originally there in your prior 2 segments. So here we can clearly see that across different segments, the interactions do not remain static, they are changing. And how does that look on the resilience landscape? So again, you have an upper attractor. Over time, as sea surface temperature increases, it hits a predicted tipping point, and it folds onto the lower attractor and starts moving forward again. So combining insights across systems. In the positive takeaways is that it can approximate non-homogenous ecological processes and recover ecologically valid links. The change point processes are intuitive, and it can elucidate previously unknown resilience dynamics. These are all great things. However, there are some problems that I will talk about. As system complexity increases, the signal to noise ratio becomes more apparent. So with the rocky shore, no matter how many breakpoints I put in, it always converges to a singular one. But with fisheries, you can clearly see it's a lot noisier. And this is only when I set, say, 2 breakpoints. You can set 3, 4, 5, and you would imagine that, okay, if these were valid breakpoints, then even if you increase the amount of breakpoints, they should still converge to these peaks as well, right? But what actually happened, what I found to happen was that when I say, oh, I'm going to increase it to 3, you start seeing random breakpoints appearing up here that didn't appear in the original in your original, and this continues to happen as you increase the number of breakpoints. So with network complexity and system complexity, signal to noise ratio becomes a problem. And how do we then standardize this if we wanted to move on this framework, right? So, and secondly, identifying thresholds via resilience modeling also becomes significantly harder, because as you increase the complexity of a system, you got things like time lags or feedback loops. You got multiple feedback loops, and these things tend to attenuate responses. So identifying thresholds will probably be a lot harder. So that's what I have today.